Swayam Prabha. Digital India. Educated India.
Welcome back to lecture number 19, part 4. We'll continue with the same topic, food deterioration models and shelf life testing procedure. So in this lecture, I'll be solving a couple of numerical questions. If we take the previous lecture, a numerical question which we solved, that was based on Q10 model. That was numerical question number 4. So basically this lecture number 19 has been divided into 4 parts, part 1, part 2, part 3 and part 4 on the same topic, food deterioration models and shelf life testing procedure. So in addition to 4 numerical problems which we have solved so far in lecture number 19 in different parts, I will be solving 2 more questions. So calculate the weight fraction of ice in the food and the refrigeration load. So in the food, when 100 kg of meat is frozen from 0 degrees centigrade to -20, it is given that the moisture content of the unfrozen meat is 71.7%, that is 0.717. The initial freezing point is -1.7 degrees centigrade. Assume 0.32 kg of water bound per kg of solute. We have to calculate the weight fraction. The weight fraction of ice in the food. So let us use the notation which I have used in the PPT. There are a couple of temperatures are given. The initial freezing temperature, that is IF. This I will be taking it as initial freezing temperature. So let us write the given data. This is numerical question number 5. Given data. Initial freezing temperature is equal to -1.7 degree centigrade. T naught is 0 degree centigrade. T naught is 0 degree centigrade. That is given in the question. That is, meat is frozen from 0 to -20. 0 to -20. Let us take the temperature -20 as capital T. That is -20. T suffix IF refers to initial freezing temperature. Initial freezing temperature. So let me write here TIF. TIF is initial freezing temperature. So the moisture content in the unfrozen meat is 71.7%. So that is taken as XWO. 71.7%, which is equal to 0.717. And the water bound per kg of solute, that is the symbol used is B. That is water bound. B is equal to 0.32 kg. Unbound or the free water is the water which is referred to as the water activity, and this water bound is the opposite to that free water. And the latent heat fusion is given. Sometimes we'll take it as 335 kilojoule per kg. So here it is taken as 333.6 that is latent heat. Let me use the same symbol. 333.6 kilojoule per kg. Let us solve this problem step by step. First step is determining the effective mole fraction of the water in the unfrozen food. Step 1. Effective mole fraction of water in the unfrozen food. Okay, so there's these correlations are mathematical expressions taken from the standard literatures. So no need to see the derivation of these equations. Just we need to apply the appropriate equation based on the question which is asked. So ln of xw is equal to 18 into ln of xw is equal to, x refers to the mole fraction, w refers to the water, 18 into delta H naught into T naught minus TIF T naught minus TIF. Let me again remind, TIF is the initial freezing temperature divided by R into T naught square divided by R into T naught square. So 18 here, 18 refers to the molecular weight of water. So this is given. Even otherwise, we can take the latent heat of fusion, 335 kilojoule per kg. So here it is not given. We have taken at 333.6 kilojoule per kg. T naught is given. TIF is given. T naught again we know. So let me write it clearly because these letters are not clear. This is TIF. This is T naught square. T naught square. So T naught is given. R is the universal gas constant, 8.314 in joule per mole Kelvin. R is equal to 8.314 joule per mole Kelvin. So substituting the values, we will get ln of x w is equal to, let me see how much. Ln of x w equal to minus 0.0165. Ln of x w is equal to minus 0.0165. Minus 0.0165. So therefore xw is equal to 0.9836. Therefore xw is equal to 0.9836. Next one is finding the effective molecular weight of the solute in the food. Effective molecular weight of solute in the food. Step 2 is effective molecular weight of solute in the food. Effective molecular weight of solute in the food. The formula is MS equal to 18 into XW. Capital M refers to the molecular weight, S refers to the solute. 18 into XW into 1 minus XW naught divided by XW naught into 1 minus XW. XW naught into 1 minus XW. This is given in the problem. XW0 is given in the problem. 71.7%. This is the XW0 value. 0.717. 18 again it is the molecular weight of water. XW we have just calculated. We can substitute and find out the value of MS. Substitute the values of XW and XW0. Therefore, MS is equal to, so all the values are given, 426.6. 426. Third step is, you need to find out the weight fraction of the bound water, that is water which does not freeze, Bound water is nothing but the water which is combined with the other, which is combined chemically with the other substances. Weight fraction of bound water. So that is step 3. Weight fraction of bound water, that is non-freezable water. So that is XWB, which is equal to B into XWB. Here W refers to water, B refers to the bound water. W is water, WB is bound water. Water that is chemically bounded with the other molecules. So this is equal to B into 1 minus XW0. 1 minus XW0. B is given as 0.32. It is given in the problem. This is 0.32 kg. 0.32 into 1 minus XW0. XW0 is 0.717. That is 71.7% of moisture. The weight fraction of bound water is 0.091. That is 9.1%. 0.091 or 9.1%. 9.1%. So let us next, the weight fraction of the freezable water. Weight fraction of the freezable water. Weight fraction of freezable water. The portion of the water in the food which freezes. So that is XWF. So WF is freezable water. So this is equal to XW0 minus XWB. The XW0 is given, that is 0.717. This is 71.7%. Out of which some, this is the moisture content of the unfrozen meat. This is the moisture content present in the unfrozen meat. So from this we have to subtract the weight fraction of bound water. So this is equal to, this is 0.717 given in the problem. This we have calculated, that is 9.1% or 0.091 and 0.091. So the weight fraction of freezable water comes to around 63%. It is 62.6. That is equal to 0.626 or 62.6%. That is out of 71.7%, 62.6% of water, that is the freezable portion of the water. and the remaining 9.1% is bound water. Bound water. So we have to calculate the weight fraction of the ice in the food. So I will be using the subscript I. Step 5, weight fraction of ice in the food is equal to weight fraction of ice in the food is equal to, so that is X I. Let me use Xi. So Xi is equal to, so there's a formula XW naught minus, let me write this one, XW naught minus 1 minus XW naught into 1 minus XW naught into B minus 0.5, B minus 0.5 into molecular weight of water divided by molecular weight of the solute, which we have calculated, into molecular weight of water divided by molecular weight of solute, so this into temperature difference, TIF minus T by T naught minus T. TIF is the initial freezing temperature, the whole divided by let me write it here, the whole divided by T naught minus T. So this is equal to Xi is equal to, so all the values are known. If you see this formula, XW naught, it is given in the problem, 71.7%. B is given, that is 0.32 kg of bound water. This is the molecular weight of water. Molecular weight of water is 18. Molecular weight of water, molecular weight of water, which is equal to 18. This is the molecular weight of solute, I think, which we have calculated, molecular weight of solute. Molecular weight of solute, which we calculated in step number 2. This is the molecular weight of solute, 426.6. This is also known. TAF is given, T is given, T naught is given. Okay, so substituting all the values, values of X, W naught, B, MW, MS, TIF, T and T naught, we get the weight fraction of the ice which is formed. It comes to 57.8%, 0.578 or 57.8%. So that is what we have to determine in this problem. Calculate the weight fraction of ice formed in the food. Before I complete this lecture, let us quickly solve one more numerical question. It is almost a similar problem. Most of the data which are given for in this problem is same as that of the previous problem, that is numerical question number 5. Only thing is we need to find out the refrigeration load. So calculate the refrigeration load when 100 kg mass is given. So let me write this also in the given data. Though it is not used for the previous problem, it will be required for this problem. Mass of meat is given as 100 kg. So in the previous problem also it is given. It is given as 100 kg. So it's frozen from the same temperature 0 to -20. The moisture content of the unfrozen food is same, 71.7%. Initial freezing temperature is same. In addition to these data, the specific heat capacity of the unfrozen meat is given, which is around 3.08 kilojoule per kg degree centigrade. The specific heat capacity of the fully frozen meat, this is unfrozen meat, CP value of unfrozen meat is given, CP value of frozen meat is given. The solids is given 1.25 kilojoule per kg degree centigrade, and also for the ice it is given. Assume again the same value, 0.32 kg of water bound. This is the same number. And the reference number which is assumed for this numerical question is minus 40 degrees centigrade. So due to shortage of time, I may not be able to substitute the values or write it in detail, but the solution is given in the problem. So let us write the given data and see what formulas we have to use to find out the refrigeration load. So this is numerical question number 6, given data. So the temperatures are same, like T naught is equal to 0 degrees centigrade. Initial freezing temperature is given as minus 1.7 degrees centigrade. Reference temperature is TR, which is equal to minus 40 degrees centigrade. I'll write here. TR means reference temperature. Mass of the meat is given. Temperature minus another temperature is given minus 20, that we are taking at T. Mass of the product is given 100 kg. CP of unfrozen, that is 3.08. So I'll use CP of unfrozen, 3.08 kilojoule per kg degree centigrade. So UF means unfrozen. F means frozen. CP of frozen is given, that is 1.5 kilojoule per kg degree centigrade. The heat capacity of the fully frozen meat is, 1.5 kilojoule per kg degree centigrade, and solids is given, and also ice is given. B value is given 0.32 kg, and the moisture content is also given, so that will be XW naught is equal to 71.7%, which is equal to 0.717. So we need to find out the enthalpy at two temperatures. One is the freezing starts at 0 degree and it goes up to minus 20, which is given in the question. From the meat is frozen from 0 to 20. So the enthalpy at 0 degree need to be determined, and that will be H1, and the enthalpy at minus 20, that will be H2. The difference will give the amount of heat to be removed. Okay, M into delta H. Step 1, enthalpy of meat at 0 degree centigrade, that will be H1. Since two enthalpies are there, I will be using H1 and H2. So using this formula, enthalpy of meat at 0 degree centigrade. So CPUF means specific heat capacity for the unfrozen. T naught is given, TAF is given. TPF means specific heat capacity of the frozen meat. XWO is given in the problem, moisture content. B is given 0.32. Capital MW is the molecular weight of water, which is 18. Again, MS is the molecular weight of solute, which we have calculated in the previous problem, 426.6. And TA, reference temperature, is given minus 40. So here all the temperatures are substituted in centigrade. So the H1 is 260, around 265 kilojoule per kg. Step 2 is enthalpy of meat at minus 20 degrees centigrade. So this is slide number 10. So let me write refer calculations, refer slide 10, and here refer slide number 11. So this will be H2. The enthalpy, the formula will be slightly different. This is for the unfrozen pot. When we use the formula for the frozen pot, that portion will not be there. Only the frozen Cp value will be there. Cp of UF will not be used. More or less a similar formula. Only there are some changes in the temperature. So this is an empirical relation which has been taken from the literature suggested by researchers. So H2 comes to 39 kilojoule per kg, and step 3 is heat removed. Step 3 is heat removed. Heat removed is equal to, that is, I think I use Q. Q is equal to M into delta H. That is equal to M into H1 minus H2. M is given as 500, H1, H2 we have calculated. This is H1 264.56. This is H2. So the formulas have to be very carefully used, because in both these formulas I have used the normal bracket and two other types of brackets, square bracket also, so that the calculations are done without any error. So H1 is 264.6. So this is equal to Q is equal to M is 100 kg of meat, H1 264.6, H2 is 39. So when you substitute the values, you will get 22,560 kilojoules of heat to be removed. 22,560 kilojoules of heat to be removed. Here this is mass only, not mass flow rate. That's why we are getting the answer in kilojoule. This is in kg, enthalpy is in kilojoule per kg. So kg and kg will get cancelled. You will get the answer in kilojoule. So with this, let me conclude lecture number 19, part 4. Thank you.